Hi, my name is Peter Flemings, and my colleague Thorsten Becker and I are teaching a new course called Lab to Planet Earth Dynamics this spring. Thorsten studies global planetary convection. I study the soil mechanics of sedimentary basins, but both of us care about the physical laws that control rock deformation. And those two lines of research come together, for example, when studying earthquakes. Thorsten and I think that a key skill to develop for geoscientists is to build quantitative intuition. And we think that a key way to do this is to demonstrate chemical, biological, and physical processes in the laboratory, and then upscale those processes to more complicated geological systems, as is shown, for example, in the two images on your right. A few points. This course is intended for the second-year geophysics student or for the geology undergraduate at any point during their degree. There'll be a minimal amount of math. You'll be working with spreadsheets. You'll be using codes that we develop, and you'll be making observations in the laboratory. We're going to teach this course both online and in person in a hybrid fashion. The laboratories and the laboratory lectures will be done in person, but you can still watch from home. Many of the modeling lectures will be presented entirely online. So how are we going to do this? We're going to have 5 modules. You can look at the syllabus and see what each module is. I'll emphasize that different modules will demonstrate different Earth processes or Earth geosystems, from groundwater flow to lithospheric deformation to sedimentation and erosion. Thorsten and I thought we would give you one example, and one thing we're going to talk about is friction. You can imagine here this individual on the left is lifting up a board. Ultimately, the board will reach a critical angle, and that weight will start to slide downhill. We can do a simple force balance and demonstrate what we call the friction law, and then we can start to upscale. For example, we can start to talk about Coulomb failure through a Moore's circle diagram and think about at what stress state a rock will fail and the orientation of those failure planes. And then we can upscale it one more step and think about in the Earth the orientation of faults that will form in characteristic faulting regimes like normal faulting or reverse faulting. And finally, we really want to share with you some of the exciting dynamics that results from thinking about friction. And we're going to talk about the earthquake cycle. You can imagine a simple block connected with a spring that you pull. That block is going to move in a nonlinear fashion, and this represents the an entire field of earthquake physics, which is the study of the earthquake cycle. It all starts with an understanding of simple physics and in this case, friction. So Thorsten and I hope that you will join us in this exciting new course at the Jackson School. Thank you.